My talk is entitled Small Smart Turbines. Small you will see, smart you might not believe me, but certainly I will try to explain to you what I mean by smart devices. I'm going to go through some context, which I couldn't do otherwise. I think the context is important, so I'll go rather quickly to that bit. I'm going to have a demonstration, and it is always a bit of a risk to do a demonstration in front of an audience. But hopefully it will all work out. And if it doesn't, you just have to have a laugh. And I'll go to my main topic. My main topic is here. This is where I find the passion of what I'm doing in one area of my research space. I've got several. This is the one I find substantial passion, drive, and you'll see why. I'm hoping you will see why. And then I'll tell you about 5 innovations we've proposed, we're putting forward, some of which have been taken, might be taken further to commercialization. So that's the kind of the drive of my talk. So if I got to the context, I plotted, or rather I pinch. I didn't plot this graph, I took it. And it's a very interesting graph because on the vertical axis you will see the demand for transport. That is 1,000 vehicles, 1,000 vehicles per 1,000 people. In other words, 1,000 people, and as you go up, you'll have 1,000 will mean 1 vehicle per person, and that includes cars, trucks, and buses. So that is basically demand for transport, and demand for transport against GDP per capita. And then you've got blobs in there, or circles. The circles mean, in fact, the population. So you'll have population. Of course, we all know who this guy is, because he happens to be rather big, and they've chosen red as the color. Nothing to do with me, but it's somewhere there. Okay? China. Up there you have the United States. We sit somewhere here, Europe. You can see the color there. What that says is really, as time progresses in your economy, you will demand greater transport. And of course, we will see Africa, particularly in blue, moving probably up that scale, demanding more vehicles to be available, trucks, buses, and cars. So clearly, undoubtedly, there will be an ever-increased demand on transport. If you look at how CO2, which I'll talk quite a bit about CO2 in the next 3 slides, carbon dioxide, and what is the impact, or rather, of transport in terms of fossil fuel related to carbon dioxide, it's about 23%. And I say that in what is all about carbon, as far as I'm concerned. So I'll show you a metric you're all familiar with, a metric you see if you open a car magazine, you want to buy a car, you will see grams of CO2 per kilometer listed all over prominently in the advert. So I will be plotting in the next 2 slides grams of CO2, hundreds of units, or tens of units, per kilometer of travel. And that is a measure of how much CO2 that particular vehicle will emit, or that fleet will emit, or that country overall is heading towards emitting. So the first one is the nations. So if you look at, again, I'll explain the graph rather here. So that is the grams of CO2 per kilometer. Grams of CO2 per kilometer, normalized in some particular cycle. We don't have to get into the argument over that matter. And you'll have units of 270 down to 90. So this is not a 0 axis. This goes down to 90. Note that figure. So up in the top level, you'll find the United States, North America, where in the 2.5 decades, today we're in the middle precisely, 2000, they were sitting about 260. And that progression downwards is a pattern of all nations at a greater or lesser degree over time. So clearly a very good performance there, and a desire, because when it becomes broken line or dashed line, is a desire for the United States to deliver 107 by 2025, coming from 270 or 260. That's a rather big decrease. And CO2 is the measure you see. If you look at the bottom countries, that's where the EU sits, and Japan, smaller cars, perhaps more family cars, perhaps lesser. In Japan particularly, the driving patterns are different. And you're sitting at the bottom, and of course, you're now heading downwards, luckily, again, and the EU is heading towards 95. So legislators will say, in 2020, when you sell a car above, manufacturer sells a car above 95, you'll have to pay some penalty, because you've exceeded that particular figure of 95 grams of CO2 per kilometer travel. And of course, you began up here not long ago. So a continuous decrease of CO2 impact on transportation. But of course, I want to point to some people, and here we've got some figures about manufacturers of passenger vehicles. And this is passenger vehicles, manufacturers we all know, to some extent, more or less. And what I'm showing again, CO2, always per kilometer, going down this time to 120, because again, I'm being a bit naughty. I'm keeping that relatively high, because if I show you 0, it doesn't look great. But we will see 0 later on. If I get to it, if Peter allows me to go on for a few more minutes at the end, if I don't get to it, I'll get to it. I'll show you 0 down there somewhere. So 21% down, 13%, 14%, 7%, 25% Toyota, look at that decrease, 5 years. 2005, we were sitting here, the fleet was sitting here. 2010, the fleet is sitting here. 25 reduction of CO2, which translates to fuel economy, largely speaking. And of course, in red, you will see what they want to do, if I ever manage to get this for just a minute. There, we're back. Oh, God. Red is the actual, what they want to get to, 2010, 5 years. This is the progression over 5 years. I think that's a phenomenal progression, to get improvements on performance, this kind of CO2, over a fleet by our manufacturers, some of which are sitting. I'm seeing them at this moment. There's no criticism of anybody. They keep giving us money because this is all good stuff. It's going downwards, and it's going downwards rather rapidly. Of course, hybridization is the reason for that one. On the fleet average, there's a number of comments I can make that takes me beyond my talk. This is a good picture, I hope. Well, certainly my daughter thought it was a good picture. It's a pyramid. And in this pyramid, it has 3 layers. And I'm trying to explain, how do I count for CO2? Top is in the cloud is CO2. How do I get to CO2? Well, I get to CO2 in 3 steps. Demand. How many kilometers I've traveled? Next step. I have energy conversion. Energy per kilometer. How much energy I use for 1 unit of distance. The next one. How much CO2 is contained in the fuel? Or how many units of CO2 per unit of energy? And of course, you can then multiply kilometers by energy per kilometer. You get energy multiplied by CO2 per energy, you get CO2. So these multiply each other, and it's a good image because you see, you multiply this by this by this, you get CO2. Now, the question I always ask, which of these can go to 0? I'm a scientist after all, and we do this kind of stuff with students. Which of these guys can go to 0? Well, I can either stop you traveling, and that's going to be rather hard because I wouldn't see you here today, most of you. I can't stop you traveling. This is more about change of mode of transport. That's our mayor on a bicycle of some nature next to a full electric car developed by the college. So that's demand. I probably cannot change that enormously, or certainly I cannot make it 0. Energy conversion, well, unless we find new laws of thermodynamics, it is unlikely that I'll be able to generate the power without consuming any energy. And therefore, I am very unlikely to make that 0. I'll minimize it. So I'll make it small. And then the fuel, the answer is, of course, is in the fuel, because it is the fuel that might make possible that product of 3 parts to turn into a near 0 sum. So no wonder we're interested in 0 fuels, synthetic fuels, electrification, electricity without any footprint, and that kind of space is fundamental, because you can make that guy tend to 0, you make the whole sum or multiplication tends to 0. So it's a good picture because it allows us to think about not necessarily what is the priority, what the bits are. How do I get there? I get there through fuel, energy conversion, and demand. Now, my business is here, rest assured. I am on the energy conversion bit. I'm an aeronautical engineer, Peter. Sorry to disappoint you earlier, but I am an aeronautical engineer from a very good department. But I have somehow turned into a mechanical engineering department when I remember in 1994, can be 1984, I went to an interview, you see, in another department. I went to another nearby university, I won't mention the name of, but it's nearby. And I went, and this lecturer or professor or whatever he was, showed me, it's in July, clearing process. I don't do things on time, so I do clearing. So showed me his lab. Says, well, which of these is a diesel engine and a gasoline engine? I have no idea. So this gasoline, which one is, I have no idea. Well, take a guess. No, I don't do guesses. I didn't get an offer. So unfortunately, the aero department here had to take me. Now, as luck may be, I'm in mechanical engineering, teaching mechanical engineering students doing engines. It couldn't be more opposite of what I thought I might be doing one day. It's a little story of 1984. So let's talk about energy conversion a little bit. And this is a picture many of you are familiar with. So if we say we have so many units of fuel in that bottle, or wherever it is, this is actually water, and we want to see how much of that is converted to power at the wheels to move me forward, or backwards, but generally forward. I'll say, well, in fact, the sum is that 60% goes up the exhaust, out of the exhaust, and some of that is the exhaust, and some of that is the cooling of the engine. These engines are very hot. You can saw a picture earlier. I'll show you another one in a minute. So 60% of that precious fuel, which has been sitting underground, is now utilized to warm up the vicinity, generally, of the vehicle. 60%. 15 to 25% is in idle deceleration and pumping losses. Drivetrain accessories, you might want to have your aircon, of course. You might want to use some of that, your mobile phone, your radio, 5 to 15%. At the end of the day, something in the order of 10 to 15%, I hope they add up to 100, I'm not sure, I haven't checked. 10 to 15% is what moves you forward. And we've taken out quite a few other elements that we would like to change. So I'm going to tell you at the very end an innovation, something we've come up with to tackle some of that 60%. And my business is precisely in this space, as you will learn in a minute. So a lot of potential, but some limits by the second law of thermodynamics, some limits by our engineering ability to some extent, some limits by the fuel we're using, and so on. The fact of the matter is that we are at that kind of level. So I'll tell you about the first technology, not mine. This is well established to some extent. You can see engines are getting smaller. They are reducing their size. And here is an example of one which I've taken. This is a 3-liter machine. Liter means if you take all the cylinders as they move, we'll show you in a minute one of those, and I'll do a demonstration on one of those too. And if you sum up all the volume contained in that cylinder, that will give you the capacity of that engine. That happens to be 3 liters. And what I've done is I've made it smaller. And because I'm very naughty, I just photocopy down the whole picture. Because, of course, it's so much easier to do so. PowerPoint is a wonderful thing. So we say, in fact, this is no PowerPoint, as you can probably experience that now. We make it smaller because it's nice for me. Now, the fact of the matter, we wouldn't do that. We will re-optimize, we'll recalibrate, we'll do lots of things, some of which I'm going to tell you today. That became a 1.4. So what have I done? I've made it smaller. So what? Well, suddenly, I might have reduced the number of cylinders from 6, likely to be, to 4. I've reduced the capacity from 3 to 1.4. And in doing that, I've reduced friction. These cylinders, as they move, and you'll see in a minute, they produce friction. The valves are opening and closing. You will see those two, friction. All the drivetrain system, and particularly in the engine system, all has friction. So I have reduced the size of the engine. I've reduced my friction. But of course, I didn't tell you that I must have the same power, but my customer will not buy, won't buy yours, won't buy mine, engine. I must have a similar transient response. I must have a sensible volume and compactness. And finally, it has to be affordable. And all of these, some of which are in conflict. But this is what we call downsizing technology. You start from a larger engine, you get a smaller engine, you achieve all these attributes. And in doing so, I am increasing locally to the engine the capacity to do work. I have made it more power dense. I've increased the kilowatts, which is a measure of power, 1,000 watts, per liter. I've made it more dense. Now, to make it more dense, power dense, I have a limited amount of air. And this is, I make reference, I was talking to one of my professors, someone I respect, and he's been an inspiration, especially in the last few years, particularly in the last few years. Nick Kamsky has been an inspiration to me to have access to someone who I can talk freely about many things, including history, of course, and many of the things we talk about. And he said, well, you must tell the audience, because if you have air, you need a certain amount of air and a certain amount of fuel to deliver a mixture that can be burned and produce the output. Well, I'm telling you that because otherwise he'll tell me off. Air, fuel, mixed together into a cylinder, spark or otherwise, power. If I have a more power-dense machine, and I want the same output, surely I have to bring more air. Okay, the cylinders, fewer cylinders, so I'm going to have to fill it up with more air, because I have a smaller space. That means that I have to have external boosting. As I breathe, I am breathing, an engine is breathing as well. An engine needs to breathe in, once combusted, out. We'll see it in a minute. And therefore, when I downsize, a key attainable in technology, rest assured, coming from me, has to be, is boosting and turbocharging. Because, of course, you need to bring more air, combust, hopefully less fuel, because I've got less friction, to achieve the same output. Bring more air, combust a little less fuel than I had to before, produce an output which is the same as before. And that is the technology behind downsizing. We are downsizing all engines. The short to medium term technology is undoubtedly through this technology. Is undoubtedly something which is common to us, where mechanics can repair, where our production lines can achieve, and is undoubtedly going through that. But of course, the axis I had earlier was quite high, 120 and 90. So the question is whether I can go below that. So boosting and combustion. I didn't mention combustion. There's very eminent combustion people here in the room, so I dare not to even mention the word. Combustion, of course, a key element of this whole process. Right. This is an engine, ultraboost, at the University of Bath, collaborators. Here are some of the collaborators, many of which are in the audience. This engine aims to downsize a Jaguar, a JLR, Jaguar Land Rover engine, from a 5-liter to a 2-liter. That's a 65% downsize. That's an enormous level of downsizing. You can see red hot. I told you about heat earlier. That is glowing red. And the picture is not great because if you saw it in my computer, it's absolutely glowing red. And it aims to achieve a 35% reduction of CO2. So these are not small changes. I want to finish this part of my talk by saying these are not small changes. These are significant changes that we might think 1-2% is good. Well, here we're talking 35% aimed, and we might achieve a little less. So this is a live project. Imperial College has been engaged in selecting the boosting technology. Right. Thank you, Jaguar Land Rover, for this video. Fantastic. Cylinders moving up and down, 4 of them in line. Do it rather quickly. It's been dressed with all the gadgets that it requires. That is my turbocharger. I'll do it rather quickly. Don't worry. But I quite like it. Of course, this is what computer-aided design can do. Beautiful images of an engine. And there you are. It's reciprocating. This is what is inside in the core of the engine. And I'm starting to talk more like an engine person than a turbocharger person, but I'll rectify that in a minute. So that's my engine. Right. So this is the turbocharger, of course. The turbochargers are devices that allow you to enhance the level of breathing of my engine, how much air I bring in. It is also a device that allows you to recover the exhaust to some extent through a turbine. Compressor into the cylinder, into the turbine. And they are found everywhere, ubiquitous. Marine, not terribly exciting. Definitely not exciting. Marginally. Yeah, it's pretty good. More exciting. My students will like this one. But of course, my students love this one here. Because they all think in turbocharging 2014 Formula 1, well, Ricardo must be cool. Because this is definitely cool, right? Unfortunately, turbocharging was in Formula 1 in 1986 when I was a second-year undergraduate in aeronautics. So actually, it's not rather cool. It's just coming back to where we were. 26 million units a year or so, an enormous production rate. If you want to find a turbo machine, which is very common, a turbocharger is one. I've got one here for those who want to come later. Mitsubishi Heavy Industries, very nice machine they send me, so long as I put it on my desk, which it is on my desk, not today, but normally it's on my desk. So what I want to tell you now is about a little bit of our engines. We'll do a demonstration. Hopefully it will all work. And if it doesn't, we'll have a laugh. Of course, we've tested it. This is Imperial College. It's not going to be otherwise, isn't it? So the first thing I'll do when this is ready, I'm going to show you an engine. Most of you have seen one there. I'm going to show you one right here. It's a single-cylinder engine. I'm just going to put it here. And if those who don't want to fail to turn up to Imperial College, if they ask this question, is this a diesel engine or a spark ignition engine? What is this? Well, unfortunately for you, I have a spark plug. So it's a very easy answer. It is a spark ignition engine. So you've passed that bit of the test. I'm going to take it off because I want you to see the cylinder. And the cylinder is a device. Naturally, it's going to go up and down because I'm turning it with my hand the wrong way. It has to be this way. And it's going to go up again. Here we see it. Friction, friction, moving parts. Two valves. I'll point to them now. Two valves there. One red, painted, because it's the exhaust. One inlet, painted, which is blue, which is the inlet. Air comes in. Air leaves. So an engine will go, piston will go down. Piston will go up. Now just to get it to the right place, which must be here. The audience will tell me otherwise, I suspect. Yeah. So that valve, blue, is now, you can see it, it's lifted. So air, air will come in. So it's open, it's coming into the cylinder, it's filling this space here, but of course it's air and fuel. I've mixed it before. Air and fuel comes in at a given rate, which is ambient, through that valve into that volume, which is the cylinder volume I was telling you earlier. It comes in, fills out that volume, then it shuts. Both are shut, now closed. Cylinder goes up, it compresses. When it gets to the top, somewhere here, then I've got my spark plug, which ignites the charge, and now power is produced, so this moves down. And now the exhaust valve opens, which is the bit I'm interested in, I'm afraid, which is the bit that now happens where the valve is open, exhaust gases, which have some remaining temperature, not to say a high temperature, and pressure, expelled through that valve into ambient. So inlet, compression, bang, exit. Right, so you've never seen an engine, you've seen one today. But we now need to get to a demonstration, because of course it has to be fun somehow. And I'm going to have a demonstration here. And I've got a device which has been very nicely put together by Harminder, Asanka, Ming Yang, and many people in my team who are incredibly happy to help me at all times. Luckily for me. You've got an engine here. I will not be firing the engine with fuel. So rest assured, you're very safe where you are. There will be no fuel or flames. Because I don't do fuel or flames, despite of what I told you. I do air. I do pulses on engines. But this guy is going to be driven by a motor. We cheated, of course. We're driving an engine by a motor. And the only thing we're doing is producing pulses. Remember the valve up and down? As the valve opens, gas will leave, expand, we get out, and we'll get out along here, and we'll get out through an open end there. Okay? Along that pipe, I have a set of transducers, one mounted here, one mounted 1.5 meters, one mounted 3 meters, and I have a spare bit of pipe, a 1 meter, that I might or might not connect. We will see. So I'm going to enable the motor, so two volunteers, which I have to pick still. So you can start looking at your shoes, at the table, and do the usual. And the heads of department are not allowed to come forward. Heads of division either. No principals. You guys are disqualified from any matter to do with my experiment. Thank you very much. I have found some eminently qualified individuals that will enable all of this, which I know nothing about. Transducer will get a trace, which is white, broken line. Transducer will get a yellow trace, will get a green trace. Okay, so 3 traces will appear. This is a live experiment. You will notice because it's very noisy, so I apologize for it will be rather noisy. We will go through some speeds, 1800, 2400, and 3000. We've seen, I'm reading that bottom line there. 1800 RPM, 2400 RPM, and 3000 RPM. So I have 2 eminently qualified willing helpers here, which have to displace Peter, and they're very willing to come forward. And unfortunately, they didn't know they have to wear some of these things. And I can assure you, this is the most glamorous in the market. I couldn't get anything more glamorous than this, because they are glamorous. So Amalia will be, which is here, my first assistant, will be managing that mouse. And Lucia is going to be managing 2 things. She's going to manage a little switch, and she's going to manage this red button that you know what stands for. as I say, stop Lucia, that means you have to hit it. Don't have to do it too hard, just hit it. But that won't happen. This is a perfectly safe experiment. We've got the method statement on the table, and all of those things have been checked and signed. Okay, so we're ready to go? No, my glasses are missing, and it can be. And it's definitely less glamorous. I couldn't do the glamour of the glasses, so I have those ones. Right. So Amalia can, so we're going to start the motor. The motor will produce fluctuations, and they're going to travel down that pipe. And I will comment. But when I get to 3,000, it'll be hard for you at the back to hear me, I suspect. Right, so let's go. We'll start the motor. We can't do it because I have to flick the switch. Thank you. Okay, that's okay. It's enabled. Now we can start the motor. And it's just doing a few revs, not a great deal of revs. But I think if I ask Amalia, my first assistant, to click 1800, it will go at 1,800 RPM. So I'm driving that motor. It's a pressure trace at 1, second trace at 2, third trace at 3. And what you see is the 3 traces along with time and pressure. White is near the engine, yellow is in the middle, and green is at the far end. So we'll start with the far end. The far end appears not to be sensing a great deal of pressure. Well, it wouldn't, because it's open to ambient. So therefore, it's going to try to equilibrate to ambient. What I'm interested really is that in number 1, I want to have as much energy available for this guy, because I am doing turbochargers and turbines. I'm going to put this guy in the exhaust. So I want high degree of pressure available to do work. But also I want to avoid something else. I don't want that resonating pipe that will appear in a minute when we do the next speed. I don't want that to impair, to reduce the capacity of the engine to expel the gas. Because if it doesn't, if the expelling is not good, it's going to stay. And that whole thing is not good news. The engine designers tell me it's not good news. Said, Ricardo, don't try it. It's not good news. Because the combustion process requires you to get rid of that gas in the main, except internal EGR, if you know what that means. But generally, you want to be able to not impair. When the red valve opens, I want the gas out. So it's 2 things, maximum energy, little disturbance, maximum energy, and a turbine. So that trace, the white trace, very close to the engine, appears fairly sinusoidal, not terribly exciting. Some pressures going up to 1.3, whatever. Some suction going on there. And this guy here appears to be following the other guy. So it looks like a nice, smooth trace. So what we'll do now is when we switch that one off, we'll go to 2400. And we have different speed, different valves, number of valves, action, moving, different velocity, same pipe length. And now suddenly I'm not so happy with this trace. Because now this trace, white, has a high degree of oscillations. Just follow it. You have a main peak, a secondary peak, a third peak, and so on and so forth. Yellow has an awful lot of oscillations as well. So that, first of all, I have not promoted energy at the exhaust. And secondly, it is likely that as a wave went down to the end, it reflected, well, it's likely, no, it is exactly what occurs, reflects and goes back, and there is a continuous set of waves moving that way and reflecting back and moving that way and reflecting back. And that is the environment very often a turbocharger will experience. You see it live from this demonstration. Right, not satisfied with that, we'll do 3000. You see, 3000, some of those secondary oscillations have disappeared. It appears that the tuning of that pipe is more adequate. I have more of a band of pressure. I like it as a turbine designer. And I have perhaps fewer reflections, because as waves go forward, some come back. It is entirely possible, as some of you know, they will add up, and they add up at the right time, in the right place, promoting good turbine output, good engine behavior. So if we now turn this noisy thing back to, yeah, leave it, that's fine, that's good. And I get my other assistant who's been doing nothing really well. I don't know why I pay her. She's going to take that little bit of tune, because I'm not happy with 2400. This clearly is not a tune system of waves. I'm going to stick it in there. Thank you, Lucia. Make sure it's well tight. I'm going to check. Thank you. So we've put an extra meter. Two things will happen. Transducer 3 will react now because there's a bit of pipe behind it. And the second thing I want to see, have I resolved some of the difficulties I had at 2400? And since I was here earlier today, for the last 25 years, I suspect, I had recorded what we saw earlier at that speed. Highly oscillatory waves. We can explain which ones goes forward and backwards. No time, and I'll bore you to death, I suspect. But clearly, some waves are moving and adding and subtracting in various places. So if I close that, remember that image, we will now add an extra pipe, 1 meter, and see what occurs. You see, I came back to something that was quite similar to 3000, which I was reasonably happy with. I've now banded the energy, and I've removed some oscillations that might have been there that would have been difficult to cope with as far as the engine is concerned. I wouldn't say it's tuned, and there are some people here who know about tuning a great deal more and written books on the matter too. But I have demonstrated the impact of speed. Waves are occurring, and you can see them here. They're very phenomenal waves. 1.5 bar is 1.5 times ambient. So these are phenomenal waves which have been created by that little engine. So with that we can close up. And we flick the switch because we don't want to leave the machine on. And we will thank our assistants for doing that. Yeah. Okay, so we'll go back to the center of the talk. And here I've already shown you this, so I hardly have to go through this. You can imagine that the environment that you guys from the auto industry are asking me to design a machine, to get engaged into the science of that, is complex. Oscillations, no good. This is what for many years, I've talked about a marriage which is not great. It's a bad marriage. Because you have a highly oscillatory device which likes oscillations by nature. It is designed to be so. And this unhappy marriage makes this guy very unhappy because the turbine doesn't quite like all these oscillations. This turbine is designed to run at some particular conditions with some particular flows. This is the turbine inside the turbocharger. And therefore, there are some limits as far as how you can make the flow approach this device. And therefore, an unhappy marriage appears that I think we're trying to resolve, and we've been trying to resolve for many decades. And maybe one day we will resolve it before getting divorced. But so far, you can see the trend is towards coupling more unsteadiness, far more than you see here. The trend is to go towards more difficulties for the turbine. So we'll talk about solutions later. If we look at a simulation, this was in 2005. This is the first simulation ever conducted on a full stage by one of my students, Dean Palferman, and he simulated with CFD a full stage in full rotation. This is velocity magnitude. You see changes in color indicating velocity changes from 50 meters per second in blue to 282 meters per second, which is a great deal, in red. And the whole flow field is fluctuating and changing. Okay. Now, we took care of this simulation. It took us quite a few years because it is essential to bring experiments and calculations together. In David Gossman, we were having dinner, lunch yesterday, and he reiterated the matter that it is absolutely essential. This calculation is not that it's difficult, it's that we require experiments and boundary conditions. And you can imagine the boundary condition experiments are quite complicated. I'll show you my experimental facility in a minute. You might have two entries. You might have that guy flowing, consequence of those pulses, that guy now flowing, or not flowing, got that wrong, middle flowing, and eventually there'll be flow here and there'll be no flow here, an ABB turbine in this case. So a highly oscillatory flow field there with one side in solid, one side may well be a broken line. Pressure, temperature, and mass flow if you so wish. Highly oscillatory flow field. I'll pass this if you forgive me for that. We'll go to the, one of the messages I wanted to give some of you, if not all of you, is this. Is my machine near steady state? Can I consider the design of my turbine in a steady state fashion, and therefore say, from my pulse generated in a machine like that, I take that time, I read that pressure, I go to the map that the manufacturer has given me, acquiring steady state. And I get that pressure, I read, and I read the mass flow. How much air my engine is swallowing, how much pressure the turbocharger sees. And I say, this guy's got me the map in steady state, no change in conditions. No fluctuation change, I should say. So is that the case? If I take that and I sum it and I compare it to that guy, which is the real instantaneous event, is that a similar amount? Or if I look at the efficiency and say, well, what is the efficiency of the turbine? And I will not define. I simply say efficiency, how good it is at converting energy. Again, take the time, pressure to efficiency. Take that number, put it, I think, on this side, yeah? Compare it to the actual real trace or number. And is this a similar magnitude? Can we worry about, do we have to worry about this? Before I do that, I have to show you the facility, because there's got to be a place you take these measurements. Luckily for us, we have new laboratories down below, in one level down, refurbished. I see a photograph later. You saw it probably earlier in the video. And we have an air supply system. We have a heater. We have some pipes, some ducting. I have a device called a chopper plate, well established, well known, and I think reasonably renowned in this space. I have a turbine, which is a device I want to test. I have a dynamometer, which I'll tell you more about it in a minute. I have a device, which is not that one, which looks rather good, actually, that one there. I have a set of plates with openings. The openings are in line with the pipe, it has flow, no in line, there has no flow. So I'm able to do on, off, continuously at a given frequency. 20 hertz, 100 hertz, whatever is the time domain that I choose to evaluate. I produce pulses. I produce changes in mass flow, pressure changes and changes in mass flow. So I'm capable of shaping this pulse, taking an amplitude and changing the frequency. I have control. This is not an engine. And there's lots of engine people here. This is a replicator of pulses. An engine is another machine I showed you earlier. This is a replicator of pulses, but it's on pulses that are representative of an engine behavior. So I have a dynamometer, and this dynamometer was first developed, well, we got the money to develop it. Professor Keith Pullen, who's in the audience, and myself got an EPSRC grant to do this, 1999. And we developed it. It took 3 years. Sindri Simko is here, who's the doctoral student who did most of the design of this. And we have a dynamometer. The dynamometer is capable of taking a turbine. You've got one here on the table. And you are capable of measuring all you need to measure to know its performance at all possible quantities required to do so. I have a plot where I want to show you the output before telling you another story. I have a plot here of power of that turbine. 50 kilowatts peak power available also. Just about, yes, 50 kilowatts it is. Available. That's what came into the turbine. How much did I develop? Well, I delivered or developed the black line. And I'm plotting it against time. It happens to be degrees of the pulsator, but you think about time. So the deficit between what was available and what I delivered is something I'm trying to erode by good aerodynamic design, by good implementation of a mixture of calculations, and in my case, particularly measurements you see here. So the dynamometer is capable of measuring, is capable of analyzing, and so much energy came in, so much energy came out. So I can improve the machine. See, in 1999, when I first got this award, I remember being called onto my head of section, someone well known to most of us, Professor Jim Whitelaw, and he said, come here. So that's trouble. You got some money to do some instruments. I said, yeah, Ricardo, it won't work. Well, thank you very much. And that's wonderful. I mean, you're always right, of course. And giving me full confidence here. Ricardo, it won't work. It is not possible to dissipate 50 kilowatts in a space such a small. I know convective heat transfer, blah, 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 blah. But nevertheless, you got the money, go ahead and see if you can do it. Of course, we had done experiments before. We're not foolish. And you couldn't be foolish in front of Jim anyway. you had done some basic experiments. So he said, and it's a good story because I think ends well. 5 years later, 2 years after we should have done it, of course, a bit of delay, took a bit of effort, and it was a bit of a challenge. So Keith Pulling and myself did get it to work, and we do dissipate 50 kilowatts. The principle being nucleation boiling is nothing to do with convective heat transfer. Professor Whitelaw said, well, I'll give you that. You were right and I was wrong. Now go away and exploit it. Now use it. Now take advantage of it. And he wrote some words recently, which I want to acknowledge him at this moment. He dedicated a book to me. I have some words, but this is someone I treasure from someone who was an inspiration to me in the early part of my career. So we've done a bit of that, and I don't know which way I'm going now. There. Now we look at the output. So I posed 2 questions. The questions were, is it quasi-steady? Can I consider a succession of steady states or not? I'm going to plot here what it means to be quasi-steady. Mass flow against pressure. Pressure generated and mass flow. If I consider it to be quasi-steady, I ask my collaborators to give me a map of a turbine, its behavior, its characteristics, and I plot it, mass consumed versus pressure. And effectively, this is what I think I would be doing, going up and down that line. Now, fortunately for me, we had a facility capable of measuring. Instruments are key to experimentation. And of course, I was capable of saying, hey, chaps, experimentally, the evidence is that the machine follows a completely different trace. Luckily for you guys, it doesn't circle, to some extent, the steady-state equivalent. So it is indeed true that the machine, when mounted, will follow some trace that will encircle the steady state. Now, of course, I wasn't the first person to do this. There were other people, particularly UMIS, that had done some of this work previous. But we did a detailed evaluation here, and we've been pursuing that line of science for quite some time. The reason for that is, of course, just like, the reason for that one, I got that lost there. Because I had a very nice trace. What's happened now? This is terrible. So what was a nice trace is now turned into a real mess, right? So that nice trace is what we had earlier when I had a low speed. It's a very smooth line. It's a nice line. It's a sinusoid. And it happened to be when this guy was running at whatever speed was, 1800 it was. But of course, when I went to 2,500, I started to get some sort of complicated traces of fluctuations of pressure going this way, pressure going that way. And it becomes something which even when I used to say, when I used to give conferences, when my daughters were younger, I used to say my daughters were capable of drawing because they could just scribble anywhere. But in fact, it is a repeatable experiment. It is exactly the reality at 80 hertz, which I think I don't have in the slide, due to these fluctuations. Okay, let's move to the next. So you don't follow the steady state. You have a state in which the turbine needs to be filled. So it is filled, and here it's empty. So it has to swallow more mass because that pipe, the manifold in the case of a turbine, this guy here, in the case of a turbine, needs time to fill up and then it needs time to empty. That's called a filling and emptying state. So really, mass flow, you would not match the steady state equivalent. If you look at efficiency, you've got a vertical axis of relative efficiency because I can't give you the actual value despite of asking. It doesn't matter. I just want you to compare that line, presuming a succession of steady state, to that line in blue, which is the real instantaneous evaluated turbine output efficiency in the facility. The frequency is in reverse. For some reason, no one understands. 42 hertz here and 84 hertz here. And you can see that, of course, there is some substantial capacity for improvement. So there is another innovation we'll talk about in a few minutes. The reason for that, to some extent, is that if I have a turbine and I want to ensure the flow is good, and because, of course, I studied at Oxford, they taught me about turbomachinery. So Professor Terry Jones cannot be here, but of course I like to acknowledge him. So I learned turbines from him. Of course, they were big turbines. He never told me you might end up working in small turbines. You know, I did big turbines for roles in the center of technology there. But I ended up doing very, very tiniest turbines. So there is my turbine. Can't see it from the back, I suspect. I've got a big pen. And if the flow came in at an angle, this guy would rotate naturally, because I'm blowing on it at an angle. Okay. And there is an optimum angle, happen to be minus 30 degrees, bear that in mind, minus 40 degrees, negative meaning this way, don't worry, not that way, that way. And I want to now experience experimentally how would that approach angle would vary during the real experimentally measured velocity field. Oh, sorry, I jumped that. Right, and that's what you see. This is the angle of approach. Don't worry about the other lines. Green, I see green, you probably don't see it, I'm pointing to it. It's swinging from one side to the other, and while the pulses are coming, this turbine is being pulsed in the manner we seen earlier, and that triangle is swinging. And remember, minus 30, minus 40 was a good angle. And there will be a question at the end of the lecture as to anybody who can tell me why it's a good angle. I'm sure some people will tell me why it's a good angle. So that's a bad angle. That is a good angle, minus 30 degrees, minus 30 degrees, minus 40 degrees. Optimum incidence. That means that the flow is aligned to an optimum direction that enables you to have good energy conversion. And yet we've just seen that that triangle is all over the place. During the pulse, it is moving to the left, plus 32, plus 28, precisely when I have most energy. And it turns into minus for a minor period of time. So these guys really have made an entire mess of my turbine design, because it is being pulsed to such an extreme that you're bound to get what we call flow separations, and we show you a very brief picture of that. So you see the energy was here in the pulse. Remember this trace wasn't terribly dissimilar to what you saw earlier. Well, I remember because I've been looking at that pulse for a while. And you know, that pulse wasn't terribly dissimilar of energy in this case. And that is 80%, it's not pressure, it's energy, 80% of the energy content. 20% remains here and here. So 80% is there. Actually, what the greatest efficiency is not where I have greatest energy available. In other words, I have a desire to move that peak of efficiency somewhere in the space of maximum energy available. And the consequence is, of course, the overall sum is not as good as it ought to be, highly dependent on frequency, length, and all the things we've seen. So it's a desire to improve the turbine, which is what, as an aerodynamicist, I being asked, or I like doing, rather than being asked to do. I like doing. You see the flow under some particular approach velocities, and remember what I'm looking at one of these passages. It's very hard to see, I don't have time to see the visualizer. Well, I might have time to see the visualizer, why not? Visualizer is good. I like visualizer. So we'll look at it here briefly, very briefly. So we don't want that. And you will see that, in fact, the turbine has a blade, a number of blades. And it depends on the approach to this blade. I might be able to convert energy or otherwise. You can see this is the leading edge, the trailing edge, the blade surface. I have a number of these passages. This is an aerodynamic passage. And as I come to that passage at an angle, I might or might otherwise achieve work extraction. What I show you just now is a complete swing from one extreme to the other extreme in its performance. So what we'll see now here in this small one slide, we will return to the flow field, and I will just do it briefly. Again, it's a calculation in this case. And it's a calculation that will say, at this particular angle, which appear not to be good to most people, hence my question at the end of the lecture, if anybody knows the answer, appears not good, it is good, and what appears to be good, aligned with the turbine blade leading edge, it isn't good. Now this machine is rotating, let's give you an order of magnitude, at this one here, let's pick this one. This little machine, you can hardly see because it's really even difficult for me. It's a tiny little device you see on your 1.6 liter diesel, 2 liter diesel, you see this. It is spinning at 3,666 revolutions every second. 3,666, I'm told. That means that spins 3,666 times in approximately the time I've just moved my finger over it. It is a very high speed device, extreme speed device, 220,000 RPM. And what you'll have is a very strong Coriolis force. I've given away the answer, I'm sorry about that. I couldn't do otherwise. And I've got a strong Coriolis force. And that means that, in fact, that is good, so that is bad, this is good, even though it doesn't appear to be aligned with the flow. With the blade, not with the flow. Done that, we can calculate, two slides before I go to innovation. I can calculate, I can have a simple model. Aaron Costali is sitting in the audience. You don't have to model the 3D and all the gadgets. You could do that, and we've done it, I'll show you. You can do a simplified one-dimensional model, reduce order model, and get some degree of information, which is highly valuable to the designer. Right-hand side, calculation, left-hand side, experiments. A few seconds to run. We've discretized a pipe similar to that. We just recognize that there is a time for a wave to propagate along that duct. It is relatively straightforward. That is common today, but it wasn't common in 2005, 2006. Now it's a common standard procedure because it is an easy thing to do, which will not take a great degree of overhead on engine design. So if I go out of all of that, I don't know how that happened, but I come out of all of that, I get to 5 slides before I give thanks to a number of people that I must. First one, aerodynamic design of blades. If I'm able to do what is on the right-hand side, there, and move the black line to the left, becoming a broken red line, I would have been able to achieve some of the purpose that we had earlier. Had a design, radial turbine, which I'm holding. I'm going to change the blades, and I'm going to make it into a mixed flow turbine, where the flow comes at an angle. And I shift it to the left, and thus I move the peak efficiency elsewhere. I got from that radial mixed flow, achieve the mixed flow, from the radial. The flow comes in this way, the flow comes in along that diagonal. I'm indeed capable of doing that, and if I do so, I move partially that peak in the area of greatest energy potential. Because in this area, I have a particular value of that axis. I will not describe in great detail, something in the 0.6. And in this area, I am closer to 0.6 than to 0.7, which happens to be a radial turbine. So by aerodynamic design, we had several generations of these machines. They are common in the market today in some applications. They are common. And some of the work at the University of Bath, Frank Wallace, who passed away, he is one of the fathers of this whole space. And he had some proposals on this some years ago. But we've improved, we've moved the peak, we're capable of recovering greater amount of energy. But of course, I have some control engineers in the room, I suspect. I think they are. And they'll say, well, why don't you actively move something? Because, of course, if your machine is static, sorry, it's not static. I said a minute ago it was rotating at 3,000 RPM. It's not static. This is rotating. But this machine is designed to be continuously rotating at that speed without mass flow and pressure. But it's oscillating. So why don't I come up with a new concept? Why don't I let my oscillation here of that vane follow the engine pulse? So that's what I do. I will oscillate that guy to the same frequency and whatever amplitude I come up with to follow that guy. We call that active flow control. It doesn't need external power. You might do it passively. Let the flow open the vane and close the vane against a spring either way. You could do that too. We call that passive flow control. 2 patents on the matter. And I'm glad to say there is a large company, I can't say even the continent where they are. I've been told not to say anything. Innovations is sitting here, somewhere near. I can see them now. They will quite thoroughly tell me off. It's being evaluated at this moment. 6 years, 7 years of development. Apostle Spesiridis, I mentioned him alone, was behind this concept. Believe me, no one has thought of it. When it is so obvious to me today, I'm hoping it will be so obvious to you after this talk. The gains are shown, I'll go back. The gains are shown here for those really who want to take notes and want to get an A star on this particular part of my talk. They're all there. Another innovation, I'm getting to the end. Very many times, engines, you need to take some gas before it enters the turbine. This is the wheel, the rotor I've been holding in my hand, and do something else with it. It's called exhaust gas recirculation. And you want to put it back into the inlet. This is the most strange thing I've ever seen. But you take the exhaust, you put it back to the inlet, into the combustion chamber again. So it's a bit odd. But if you look at the emissions, NOx particularly, NOx, these things are improved when you do so. I make it look a bit foolish, but it is very common technology. and it's one that is not optimized as far as the turbine is concerned. You just take it off a T-junction here. You have a bit of plumbing here. And then the remaining pulse, which is being disturbed, is being reduced. You let it to the turbine and do some work. Well, we propose to have an asymmetric double-entry turbine. Put 2 entries, but you have a sector, which is the sector in which you have diminishing EGR, sort of diminishing flow, increasing EGR. You take away more here. You take nothing here. And therefore, you're capable of re-optimizing this sector on your wheel. And you can do so at different rates of EGR, exhaust gas recirculation. That is another innovation that is tackling unsteady flow performance of turbines in highly EGR or relatively high EGR rates. The data, there's no data here because I'm not even allowed to show you that. There's some calculations here. Maybe innovations will tell me off after all. Nah, they don't say anything. 2 more. This is an innovation that we want to tackle, the exhaust gas, still remaining after the turbocharger. I've been telling you about turbochargers a little bit, turbine. Then there's still gas and there's still energy before you exhaust to the ambient. So why don't I design a turbine, a new turbine, which is capable of recovering loss of energy. Again, normalizing the efficiency is not 100% efficient. Would have broken a few laws at that point, but it's normalized, about 72% or so, I can tell you. And that peak of efficiency to be in a space in which there is very little pressure. In the exhaust, at the end of that pipe there, we saw earlier, there is very little pressure. It has to go back to ambient at some point. There's a little bit of pressure and loss of energy and temperature, not in that case, in the real engine, part of the 60%. So we designed this wheel. It looks rather conventional, totally unconventional. If you look at the detail, a volute, which looks conventional, is unconventional. This is experimental information. We have been able to shift the peak, or rather that conventional design, to that unconventional design, achieving an improvement which is visible by that graph, and which is being tested, and is part of a larger project called High Boost, I should mention, where we put in this downstream of the main turbo to get a few more kilowatts. This engine is about 80 kilowatts. We're getting about 1.5 kilowatts extra. Because don't talk to me about cost, which will be the question that is the killer question. But in case you want, because you're not allowed to ask questions in any case, I'll tell you that is the killer question, cost. Finally, compressors. Remember we talked about breathing. When you breathe in and out, you want to get air in, you combust it with some fuel, and then you expand it through the turbine. Well, compressors are highly limited in their range, because we're asking a lot from them. I have a compressor here as well. And we're asking a lot from these guys. And a compressor has a peculiarity that in some space, some area of its map, pressure against mass flow, it returns into a region called surge, into which you don't want to move. It's bad news. And therefore, you might want to move. Your black line is your desire as a designer. You can't touch it, so you now redesign to ensure you're within that line. So we've come up with an innovation to be presented in a month's time, less than a month's time, where we put what we call inlet duct treatment. We put some holes in the inlet there, aligned to some particular direction, and we target that flow into the regions of the leading edge of the wheel there, where this surge event is in this machine being shown to be promoted by the flow in that space near the tip and the inlet of the compressor. So lots of things there. The bottom line is you get an improvement which originally may be like that in black, and you go to the red line, and you have created some space there for operations of a compressor away from its peak. See, final slide before thanks. I told you about earlier that I've capped my axis quite wisely at about 120 earlier. We were looking at this. And then I did it at 90, I think, and then we're looking at that. But you see, we've got a long way to go, because this is CO2 against time, going a long way, 2050, and I've drawn any junction here. This is part of a Grantham Institute paper co-authored by Dave Howe, who was in the audience, and Robin North. And we said, we know this point, current fleet. We know this point, fleet average at that time, more or less. We know the EU will take us to 95 at that point. Now, this triangle is where the technology of high boost is sitting. This is where the technology of JLR, I showed you an engine red hot, is sitting in that space. Of course, we've got a long way to go, And at some stage, in some time in the future, your internal combustion engine, shown here as the ultimate, lowest possible CO2 of an IC engine, about lowest possible, you can attain, about 60. You can argue over the matter. It doesn't matter if I say to you 62, you'll accept the 65. It's in that space. Recently checked with Ricardo, not me, the company, at Shoreham by Sea. And I think this appears to be reasonable. So we've got a long way to go, and new technologies have to come in place. I have people working on batteries with Greg Offer and Professor Nigel Brandon on thermal management of those devices. Motors with Evo Electric and a few other people sitting here in the audience, where we're looking at cooling of motors. Anything thermofluidy in that space, I'm interested. Heat transfer and fluid mechanics. I cannot cover those things in the lecture today. I think I have to thank some people. This must be a mistake. But anyway, we thank all these people. All these sponsors are actual sponsors today, plus or minus. The minus is only one case. And these are sponsors of work, government, direct, European, and so on. I have to thank the winning team. You see, the winning team, I call it the winning team, because these guys came out of the group. They've graduated. Some are still with me in that list. These are the guys who made it all possible. Work day and night, support me. I supported them. They are really the winners of this talk, at least a portion of the talk, the winners of all my research over many years. Some of them were PhDs, anything above that line, more or less. These are all guys, are all PhDs, graduated with me successfully. And some others are not PhDs, postdocs, worked with me, were unfortunate enough to work with me over a few years. Of course, the current team is here. They're all in the audience. Lots of people, lots of names. You can see their pictures. Not everybody's there. Of course, I have to thank the technical support of the department and many other people I ought to thank. But these are the people that day in and day out are working in the space that I've told you about and I haven't told you about, which I could another day. Of course, it wouldn't be right if at the end I didn't thank the person that was with me since 2005. So from 2005, the best thing that came out of Imperial College was my wife, who's sitting here. So I must say, Jeffrey, the best person that came out of Imperial College was my wife. So no arguments there, I hope. Because we met here, and my wife is being in every day, supporting me with all the things that one has to do as an academic, which you have to do in order to support your research over many years. So thank you to Maria. I think we have some little sign of appreciation to give her. Of course, I have my two assistants here.